Good morning, everybody.
Hi, Daniel. Good morning.
Hello. Good morning. Nice to join to you for in this with Zoom. Nice to join with you using this platform Zoom. So the first session is going to start at 9 a.m. right?
Yes, Daniel, you're correct. We would like to thank you very much for being a chair in our event. And yes, the first session starts at 9 a.m.
I have to thank to you. By the way, there is the first presentation that it's going to that has now. I was checking the Excel file, and it doesn't have the name yet of the presenter and the institution. It's the first paper, Intuitive and Modular Software Architecture for Functional Electrical Stimulation Rehabilitation.
I believe he's here. I believe it's Antônio Bo. Antônio, could you please confirm this? Are you the first presenter of the day? Do you hear? Can you hear us, Antônio?
Yeah, yes, I think he is here, Professor Antônio.
Bom dia, Daniel.
Good morning, Paulo.
Good morning.
Good morning.
Everything okay?
Yeah. Yes, everything okay. Everything okay. Yes. Paulo is also the name of the representative of the UFR that it's helping us with the support of the LARS, right? Of the technical staff of the LARS. Paulo is also, right?
Bruno, no?
Bruno. Sorry. Yes, Bruno. Sorry. That's right, Bruno.
Yes, Bruno and Luis.
Bruno and Luis. Perfect.
Yes, it's me, Bruno, it's Luis Marcos, and Julio. Julio is currently, at this moment, he's here as an attendee.
Okay,
He's
perfect.
in the organization of the LARS too.
Okay, perfect. Thank you very much.
So good morning for every authors, and the words is yours, Daniel. You are the boss.
Okay, thank you, Paul. Yes, we have 4 minutes more.
Yes.
According
to the schedule, yes.
According to the schedule, yes.
Good evening to Antônio.
Good evening, Professor. Good evening, Professor
Hi.
Antônio.
Hi, nice to see you all. Good. Hello.
The new virtual conference allows you to participate, Antônio. It's interesting. It's one interesting part.
Yes. It would be a bit tricky to travel all the way to Natal. I have a quite complicated setup tonight because I have a baby sleeping next to me, so I had to bring my desk all over. Yeah, but anyway, I believe it's working.
It's easier they travel to Natal.
It's easier, definitely.
Yes, definitely this way.
Good morning, everyone. Before Daniel starts,
good morning.
Just to say that we are already at YouTube. If you want to share to someone, I have put in the shares WhatsApp the site for sharing this. And good luck, Daniel. It's with you now.
Thank you.
As Paulo
Thank you very
said,
much.
you are the boss. Welcome, all of you, and many thanks to you.
Thanks to you. Thanks to you. Well, we have just 2 minutes more before the start. Okay, so we can start. Welcome to the 7th 15th IEEE Latin American Robotics Symposium and 8th Brazilian Symposium of Robotics. My name is Fernando Gamarra, and I will be leading this first session of the symposium. The name of the first session is Assistive Robotics and Human-Robot Interaction. And we will have 4 papers in this first session. I would like to welcome and thank also for the participation to all the professors, students, and all the public that is following us in Zoom. And also this presentation is being broadcasted by YouTube. So we will start with the first presentation. That it's the first paper. Its title is Intuitive and Modular Software Robotics. Intuitive and Modular Software Architecture for Functional Electrical Stimulation Rehabilitation. Okay, and the presentation of this first paper is going to be with Professor Antonio Padilla. So I'm going to give the words to Professor Antonio Padilla. Thank you very much, and the words is yours, Professor Antonio.
Well, thanks a lot, Daniel. I'm very happy to be here. I'm going to start by sharing my screen. Here I am with my presentation. Yes. Can you all see that?
Yes, yes.
Oh, that's great. I'm really happy to be here at LARS SBR. A very nice event that, well, is taking this new format this year. And also to start the program with our presentation. This is a work from students at the University of Brasilia. I'm still affiliated to the University of Brasilia, but I'm now also affiliated to the University of Queensland here in Australia. So I do have a bit of a different time to me today. So in my talk, we're going to be talking mostly about movement disorders that are caused by neurological lesions, which is a very common problem in the world today. So, for instance, we all know about stroke, which has an incidence of roughly 15 million cases every year, causing, of course, lots of deaths, but also leaving many stroke survivors with different sorts of disabilities. We're also aware of Parkinson's disease, neurodegenerative disease, that despite having a lower incidence, affects a lot the quality of life of different people around the world. And another example is spinal cord injury, which is often associated with traumatic events, and is a disease that leaves often a very young and active population with a very severe disability, impacting a lot, not only movement, but autonomic functions in many different levels. So, of course, we're here in a robotics conference, but we have to acknowledge that there are many scientific domains working strongly to tackle those neurological disorders. So we have amazing work that's happening in terms of different cell therapies, so using stem cells and different techniques. We have genetic therapies that are really promising today. For both stroke and spinal cord injury, new techniques for immunotherapy, they can really change the game. For tissue regeneration, we have many applications. I'm currently working a lot with hand applications. And for hand, for instance, there are some really interesting novel surgical approaches that can really change the lives of people with tetraplegia. So that's really important. But we do believe in our team that for all these alternatives, if you don't have improved rehabilitation that's enabled by neuroengineering and by robotics, you will not be able to achieve the whole potential of these technologies. So that's the whole motivation of our team, and that's what we're working towards. I will go directly to one case example of this type of application, which is the ability of using electrical stimulation to make people with complete paraplegia, so they cannot move or feel their lower limbs, to cycle again. So this is a footage from 2016 from the biathlon competition, where we have our pilot Stefan, who has like a complete paraplegia for more than 5 years now, 7 years perhaps. That's cycling in this race for paraplegic, and he's cycling through the use of this low energy electrical impulses that actually contracts the muscles artificially, naturally, in a way. I'll try to explain a little bit. Well, in addition actually to make the move, the ability to enable the exercise of the limb is very important, because it may actually provide lots of benefits in terms of muscle mass and bone density. So this can prevent injuries for the skeletal problems as well. In terms of exercise, so we do exercise because it improves our systemic health, and that's very important for this subject as well, not only in terms of cardiovascular, but also metabolic health. It can also, of course, be fun and perhaps be used as a type of locomotion. So the way we do that, we normally use like traditional trikes. Well, we use trikes because of basically stability for these users. And then we implement a control system that has the function of basically controlling the legs that we can actually target with some degree of performance that enables performing the correct cycling movement. So in order to do that, we need at least to measure some properties of the trike. So we do have here, for instance, a wireless inertial sensor that will, let me see if I can grab my, no, I can't, to get the crank set, the pedal position. So in order, based on that, we can, in a way, assess the biomechanical properties of the user and then control each muscle. One basic property of that is actually then how to map the muscles were being controlled in order to provide positive torque to that trike in a safely manner. But based on this, we can actually have another layer where we, in addition to provide positive torque, we can control.
Sorry to interrupt,
Yes?
Professor Antonio, but we are not seeing those slides, the other slides. Yes, we are seeing the first slide of your presentation. Really? I don't know.
Sorry for that. I will just stop this sharing just a second.
Yes.
Okay. So you had only the title slide?
Yes. But now we are seeing the slides. Yes.
Okay, let's do this and then just hope that's going to be better. So sorry for that, everyone. So let me just try to get this out of my chart. There we are. And here it is. So I was actually showing this video. So sorry that you're not able to see that. So that's a person with complete paraplegia cycling. And then I was talking about how actually to control that. I went through some of these benefits of the activity and then how we do control that. So this is a diagram that I'll try to explain briefly. This is part of our control. And this is another level of control we can implement. So you can imagine that you have then a system that not only is a wearable active system, like a wearable exoskeleton, a wearable robotics device, but it's something that's inherently connected to your muscles and the way you move. And so this is actually controlled by the user, but then you can have different layers of control. So in this slide, actually, I'm showing how you could have an additional layer of control that controls the cadence or the speed of cycling. So in this case, we can have that type of performance. That was just a single example of what we can do with these technologies. So in these videos here, we just illustrate some of, sorry for that, I don't know what's happened with my slides. So in these videos here, we show other applications that can either be used to enable physical exercise by people with motor disabilities, or to be used in an assistive scenario as well. So for instance, this video on the top right, you see again a subject with complete paraplegia that's using the same technology to actually transfer from one seat to the other, from the wheelchair to the bed, and these kind of activities. Well, that's of course the core of my work. But in today's presentation, I'd like to target like one specific aspect, which is, so why do these systems are not available to users today? Because we've been showing not only ourselves, but many other research groups, how beneficial they can be in terms of the health benefits. And so what's the problem? And of course, I have to acknowledge that there are many issues for that. And some issues, they're not related to either research or technological development, but more like socioeconomical reasons and cultural reasons as well, and different aspects. Specifically for this technology, we have really hard market and regulation challenges. It's very sad that actually some clinicians, even in high-income countries, they're not aware that these technologies actually exist, and so for different reasons, it happens that we see that some subjects, they don't have access to that. But in addition to market and regulation, we do have lots of technical challenges that need to be tackled in order to improve the performance or the way actually these devices are used. There are different aspects that we could discuss, but in this presentation today, I'm going to focus on aspects that related to how we integrate different sensing modalities, how we can actually integrate that with different actuation systems, so more like a wearable robotics perspective, and how we can actually improve the interface. So the person is controlling his body, so how can we improve that? And what we're doing and what we're building, and that's our vision, we're building a modular and intuitive architecture that's based in ROS. And well, we're doing that for different reasons, but also our previous experience in ROS as well. But then the general idea is that based on this, we're going to be able to integrate these different elements that may be sometimes common in the robotics world, but not that common in a clinical rehabilitation scenario. So of course, normally we have stimulation in clinics, but they're not the same stimulators that we can connect to a real-time control system. In that diagram, you can see that we can use different types of sensors and to interface with the user. And not only this user may be used, the sensor, sorry, as a feedback signal for your control system, but also we see those sensors are being very important parts of the control interface. So for instance, in this example here, what we have is either simple wireless inertial sensors or EMG signals that may be used to control this type of wearable systems. So what we have here in this figure is a way of actually using that to trigger different stimulation or robotic commands that will move your hand or move this robotic hand. So we understand that this could be all integrated into this system. What we have described in this paper is actually a limited version of that we are working at that time of submission, actually, where we were not using an embedded system. We had this system running in a laptop, and we were using that for actually that case study in FES cycling. So what we had at that point was this setup. So we had updated the mechanical system as well. So you can see that the track is a little bit different, and also the foot support as well. And then you have in this computer here a system that is ROS-based, running all the nodes that connects to our hardware, and actually runs both the control law and the interface. And there you see the RKT graph, just to give an understanding of what's going on behind. This is a brief example of some of the interfaces we were evaluating. This was a very important step to us, because even though we not believe that this was something that's going to be delivered for the end user, and the end user for us will be either the clinician or the patient, but it's a very easy to approach interface to design, and actually to discuss with them what could be useful in a real life scenario. Because sometimes just by discussing with them, of course, they want all the information, but they can be just overwhelmed by the amount of information and not be able to effectively control themselves. So, and of course, some of the ROS functionalities make it all much easier for us, for instance, for data logging with ROS bags as well. So I'm really sorry for the problems in the start of my presentation, but I'm getting to the end. So what we have so far right now is a successful conversion from our previous system to a ROS-based system, including that validation of not only the overall functioning, but also the interface aspect as well with end users, clinicians, and persons with disabilities. And we're doing different types of developments. So we're adapting this to activities like walking, but many other activities that we're currently working already. And these particular students that are involved in this work, they actually building the end part of it, which is the interface that can be delivered for end users as well, which currently is a Android version interface. I'd like to end my presentation with one additional remark. So the conference this week has a very good timing. So the Cybathlon happened in 2016 when we had, of course, a different world. In 2020, that's the second version of Cybathlon. We'll have they call the Cybathlon Global Edition. So it's going to be a virtual event. And again, we're going to be the only team in Latin America that's competing in the event. Our pilot will be in Brasilia, while competing with pilots from all over the world. And that's the schedule for our participation in the first round. So I hope to see you there. Thanks.
Okay, thank you very much, Professor Antônio, for the presentation. And we are going to pass to the second phase of this presentation, that are the questions. We have some questions here for you. The first one is a question of Professor. The first one is the question of Professor Paulo. He was asking, how do you deal with the limitations of the ROS in real-time application? Is it a problem for you?
It may be a problem for some applications, but so far we are dealing this with in different ways. So basically what happens is that our endpoint stimulator, it has, of course, a low-level control loop as well. So we have strict hardware time control at the end effector, let's say. But depending on the type of sensor, we may have, well, some issues. But we have to consider that we're working with a very slow system. Stimulation in itself is something that runs in 50 hertz. So we cannot actually apply any pulse faster than that. So, but for actually to recording stimulation, especially if you're using other types of sensors. So normally what you're going to have is a pre-processing of information in your hardware device that's actually sent out to ROS. And this is also not to demand a lot from the embedded system. The ideal scenario is that we could actually deliver a Raspberry-based system to different users, and they could integrate different types of hardware they wanted to use. And then, of course, not demand a lot from that device.
Okay, thank you. Do we have more questions from our audience? Let's see. Somebody's raising his hand, maybe. Well, I would like to thank you for your very interesting work, Professor Antonio. I would like to ask you just a question. It's related with the. It's possible also with sensor Kinect measure the joints of a person using the Kinect sensor, and through the joints you can reconstruct the skeleton of a person, and we can maybe detect some gestures. Are you also, Ross has some software like Hector's some software that can integrate SLAM with can integrate the Kinect with Ross. Are you planning in the future to use Kinect maybe in a way to help to integrate with other sensors?
Yeah, that's a very good question. So what we have done in the past is that I have integrated Kinect in human-robot interaction scenarios involving FES, not using ROS. It was a specific implementation. I do understand that for some of our applications, Kinect's performance, even though I have not evaluated myself, would be reduced by the fact that we have mechanical systems that are coupled to the users. So if you have, like, let's say, a floating user that's standing on a trike, or a rowing indoor rowing system, or sometimes you're walking, but you're walking with a complex walker, not a very simple walker, but a walker with systems and cables and stuff. I see that Kinect wouldn't be that good. But one thing we're using a lot these days, so we're using OpenPose, which is that library from Carnegie Mellon University. And that provides a very good way of actually data logging experiments. It has shown to be a little bit more robust to these different devices. We have tested with prosthesis users, and it didn't work because it's a prosthesis, so it's not human. But we have used with lots of patient data, and the performance was pretty good. Of course, it's limited in terms of, well, there are limitations, but we have a good experience with that.
Okay, thank you very much, Professor Antonio. We have any more questions from the audience? I think we don't have any more questions. Well, thank you very much for the paper presentation, and good evening there. We are going to pass to the second paper. Thanks to you. Well, the second paper of our session of assistive robotics and human-robot interaction. The title of the second paper is Robotic Assistance for Autism, a Literature Review. And the presenter is going to be Isadora Ferrão. So it's Isadora here with us, please.
Hi, Fernando.
Hi.
Isadora is not here, but she sent us a message asking us to play her video. So we're gonna do this right now. I'm gonna also provide a link to the YouTube for everyone that wants a better quality of the video. But anyway, we're gonna play the video right now, okay?
Okay, thank you. So let's start then with the video.
Hello, I am Isadora. I am a master's degree at University of São Paulo, and today I am going to present a review of literature on robotic assistance in the treatment of autism people. Starting then with the main factor that motivates this research. The research points to a significant increase in the percentage of
Sorry, but we are not hearing now.
I think the playback has stopped. Just a second.
Okay. Okay.
Júlio, acho que o vídeo parou. Mas o áudio estava bem. Estava assim.
People with an autism spectrum disorder, the Center of Disease Control and Prevention in the United States conclude a survey that there is one autism child for every 59. The previous number was 1 for every 68, referring to 2012 data released in 2016, representing an increase of 15%. But what is autism? Autism spectrum disorders, ASD, is a set of neurologic development disorders that affects
the audio is not working.
reproduce
Parou mesmo o áudio, viu?
Okay.
using and stereotype behaviors. Common symptoms in ASD children are avoiding eye contact, difficulty understand of other people's emotions, having strong sensory reactions, for example, feeling uncomfortable with objects they want and having obsessive interests. Although autism is incurable, it is believed that early intervention programs can help in skills. Therefore, intervention program can be introduced from children so that children can have a better quality of life as they grow up. For adequate treatment, doctors and occupational therapists (OTs) are necessary. However, the number of these professionals is scarce despite an increasing number of autism people. To overcome this shortage, researchers and engineers are making efforts in the field of robotics through in the inclusion of robotics and tools to contribute to advancing the treatment of ADS. Studies have shown that the interaction between children and the robotics have results to help children with autism and improve their quality of life. Therefore, based on our literature review, some research points have been identified and will be discussed through this presentation. We believe that this review of robotic research for children with autism provides useful information about previous work on various aspects of HRI, improving the communication with people with ASD deficiencies. Besides that, helps future research to identify potential areas that been explored in the hope of closing existing points. In addition, we also hope the information the population about existing treatments and tools. A systematic review aims to identify, analyze, and interpret all available evidence regarding a particular research question in an impersonal and repeat manner. It is possible to suggest areas that should be investigated and clarify the state of art for position of new research and examine empirical results. In this review, the main objectives were identify works that study autism related to robotics, identify the status of the art, identify the techniques used, the existing tools, and identify and assess gaps. For the definition of search sources, the following parameters were verified: coverage, availability, versatility, and sporting results, and usability. For coverage, only search sources that returned a considerable number of updated and fully accessible works were considered. For versatility, searches were selected that supports work in an automatic way. Finally, the accepted search engines were also considered using the usability criterion that is used to understand and operate. Based on criterion, the bases selected were Internet Explorer, Digital Library, ASM, and Scopus. The languages determined for review are English and Portuguese. The inclusion, exclusion, and quality criteria were defined during planning in order to guarantee the credibility of review, keeping the focus on selection. The inclusion criteria for identify studies were autism linked to robotics, social robotics with autism, and relevant studies about autism. The defined exclusion criteria were studies that not have a clear structure of objectives and results, studies that are not relevant to the main theme, studies that not have an objective methodology, incomplete studies, and studies that are not written in English or Portuguese. The stage of carrying out this review begins with the process of identifying the primary studies using the preview defined search strategies. In this way, search strings are initially created from the keywords. The second step consists of the preliminary selection of articles by reading the titles and the abstracts, and also evaluation the works fits the inclusion or exclusion criteria. As a result of the search, the total of 413 articles were identified. Their information was exported from the database in bibliotext format and imported on the Percival platform after removing the duplicate articles identified by the tool itself. The duplicate articles identified by the tool itself. 364 works remained, 49 of which were duplicate. Based on the literature review, 3 points were identified: diversity in research focus, lack of contributions, reduced duration of interaction experiments. Despite considerable efforts of development of robots for children with autism, the contributions of the works focus on behavioral aspects such as improving communication skills, social interactions, and stereotypical behavior. Another point of diversity is the choice of robots that are used. It's found that each robot has different strengths and weaknesses. In the duration of treatments, most of the research has been introduced in a short-term intervention. The short and long-term intervention of robotic intervention programs are important aspects to ensure that children obtain sufficient exposure to the robotic in terms of behavior improvement. Despite considerable efforts in the development of robotic tools for children with autism, our literature review did not find contributions to stereotyped behaviors autism deficiency. Finally, conclusions. 3 critical research points were identified: diversity in research focus, lack of contributions, autism stereotype behavior, and the duration of experiments. Thanks.
Okay, thank you very much to Isadora. So we are going to go to the questions now. Sorry. Do we have some questions from the audience? Or maybe in the YouTube channel, please?
I don't know if Isadora is online. I think not. She told us she would be here to answer some questions. However, if someone wants to ask her, please get in touch with her after.
Yes.
Okay. Thank you.
Yes. Yes, I think she's not online. Thank you very much, Professor. So we can go to the third presentation. Then the title of the third paper is Development of Human-Robot Communication Technologies for Future Interaction Experiments, and the presenter is Ana Cristina Campos from the UFMEG. I don't know if it's Ana Cristina is here, right? So
yes, I'm
would
here.
you like to present? Okay, so would you like to present with your?
Yes, let's present.
Okay, thank you very much.
See me?
Yes, we can see you.
Okay, I'm going to share my screen. One moment, please.
Perfect.
One moment, please. Can you see my screen?
Yes, we can see your screen. Thank you.
Okay, thank you. I'm gonna start. Hello, everyone. My name is Ana Cristina, and as Professor Daniel said, I'm going to present the work development of human-robot communication technologies for future interaction experiments. When we talk about interactions between humans and robots, for example, one of its main aspects is the communication between the agents. We can classify the types of communications as explicit or implicit communications. The first ones are more direct types, such as voice, gestures, and other explicit signs. And implicit communications are the ones that need context to be understood, such as facial expressions, emotions, movement, and gaze direction. Because it is so important for interactions, we want to investigate how the type of communication affects human-robot interactions. And that's the question that motivates our work. But before we can conduct experiments to investigate these effects, we need to equip the robot with tools to communicate naturally with humans. Many works integrate the perception and production of different types of communications in platforms to be used in human-robot interaction experiments. With this in mind, our objective is to develop abilities to perceive and produce selected natural human communications. We aim to create systems with satisfactory performances that can be integrated and used in future experiments. Among the desired features are accessibility and low cost of equipment and no sensors attached to the human body. The first communication we chose from human to robot was pointing gestures. It is an explicit communication and we use it to indicate objects or regions of interest. Our system tracks the joints of the human kinematic chain. We used Microsoft Kinect and a ROS application to track 15 joints, including hips, elbows, and hands. The first thing we need to do is to recognize a pointing gesture. For that, we use the distance between the hip and the hand of the human. You can see here how the distance changes when the person is standing or when she's pointing. And we compare the measured distances with predefined limits to identify if the person is pointing or not, and if it is, which arm is being used. If the person is pointing, we use the points of elbow and hand of the pointing arm to define a direction for the gesture, and with the points on the arm, we create a line to represent the gesture. But now we have to interpret the pointing gesture. We start by modeling objects or regions of interest as boxes composed of 6 planes. The normal of the planes point to the interior of the object, just as the figure. And we use these planes and the gesture line that we created before to interpret the pointing gesture. We obtain the crossing points between the line and all the 6 planes of each object, and we use plane-to-point distances to check if any of these crossing points is inside the object region or not. If it is, then the object is crossed by the line, and it is a possible indication of the human. If more than one object is crossed by the line, then we choose the one that it is closer to the point of the arm, because the further ones could be occluded by the closer one. And that's how we interpret the human's pointing gesture. As an implicit communication from human to robot, we chose gaze direction. We can use it to interpret the human attention focus, for example. Using a camera to capture the human face image and already existing algorithms, we obtain rectangles for eyes and mouth in the human face image. And with the eyes rectangles, we estimate the position of the iris centers. We also implemented Kalman filters to deal with detection failures. And with all that, we end up with the points of mouth and iris centers in the human face image. Assuming that the human does not translate with respect to the camera and that head rotations have low amplitude, we propose some geometric analysis to estimate the human gaze direction. For the rotation around the human's y-axis, which means that the person is looking left or right, we use the horizontal distance between the iris centers. This distance measured on the camera frame changes when the person is looking left or right. And we use that difference to estimate the rotation angle theta. We use the horizontal mouth displacement to decide if the person is looking left or right. For the rotation around the human's x-axis, which means that the person is looking up or down, we use the same approach, but now with the vertical distance between eyes and mouth. The projected distance also changes with the head movement, and we estimate the rotation angle phi. Again, the mouth displacement, now the vertical one, decides if the person is looking up or down. With these angles, and assuming that the gaze is always in the direction of the z-axis of the human frame, we create a line to represent the human gaze. With this line and the objects and regions of interest modeled as before, we can interpret the human attention focus just as we did with the pointing gestures. Now, to play the role of robot in our future experiments, we chose to create a virtual agent. We use pre-recorded audio files to create its voice, to provide the useful information during the interaction with humans. We also created images with different facial expressions to convey emotions. The virtual agent's eyes blink and its mouth moves when it speaks, so to convey some vivacity. The virtual agent can also direct its gaze, and we use projective geometry to transform the original face images to simulate the head movement to represent the gaze. We also divided this movement in two rotation angles, phi and theta. This is an example of the virtual agent's gaze. We can use it to convey information about the virtual agent's attention focus to the human during interactions. We evaluated our pointing gesture system with an experiment. 9 subjects executed a sequence of 10 gestures that could indicate one of 4 objects or none of them. And the system should indicate if the person was pointing to one of the objects, and if it was, which one of them. The mean success rate of our system was of almost 78%. The false negative rate, which means that the system do not detect an object while the person was pointing to one of them, was of 32.2%. We had no cases of false positives, and only once the system indicated an object while the person was pointing to a different one. And this happened with 2 objects that were intentionally positioned to represent an ambiguity, just like the one illustrated by the figure, where one object, the smaller one, is occluded by the other depending on the point of view of the subject. We attribute most failures to occlusion of the pointing arm and measurement uncertainties. We also tested our final implementation of the facial points detection algorithm. We used 7 videos of 2 subjects, executed a fixed sequence of head movements, and we calculated the mean error for the 2 distances of interest. For the horizontal distance between the iris centers, the mean error was of 0.52 centimeters, and for the vertical distance between eyes and mouth, the mean error was of 0.67 centimeters. Here we have some examples of errors that we observed. Green rectangle indicate the detection of an eye, and red rectangles indicate detection of mouths. So in the first figure, you can see failure in detection of some facial attributes, one eye and the mouth. In the second figure, you can see the mouth is not detected and one eye is detected twice. And in the third figure, you can see one eye detected in the wrong place. We force the reinitialization of the common filters in some cases, so the system can recover from errors just like these ones. We consider the performance of the facial points detection system and the point and gesture system as acceptable for our intended application. We are currently testing our gaze estimation algorithm, and with all the systems implemented, our future works include their integration and their use in experiments to investigate the effects of the type of communication in human-robot interactions. We can, for example, compare the interaction when both human and virtual agent use only explicit communications, such as gestures and voice, and when they combine them with implicit communications, such as gaze direction and facial expressions. We thank CNPq for the financial support, and thank you for your attention. If you have any questions or want to talk about the work, you can also contact me by email. Thank you.
Okay, thank you very much, Ana Cristina. So we are going to go to the questions now. Okay. Let's see if our audience have any questions. Okay, we have a question here from Professor Antônio Padilha. It says, any plans for incorporating the hand for the pointing gesture? Imagine, for instance, the user with the arm on full abduction or elevation, but the finger pointing down. That is the first question.
We do not have this plan now, but it is very interesting because we really do not consider the hand gesture. But for now, we are interested in the interaction. We want to investigate the interaction. We do not need very strong and very robust systems to do that. We can only use satisfactory performance systems that can, so we can make these experiments to evaluate the difference in the interaction. So for now, this is not in our plan, but yes, we only use the arm gesture, but knowing that, we are going to force the subjects to do some things in the experiment. For example, we are going to put objects far away from the subjects, so they are more forced. They are forced to use their arm, for example. So because that's not our point, we do not want a very strong and robust gesture system. But yes, it is a very interesting point.
Okay, thank you. And we have some comment from YouTube also, from Professor Eduardo. Maybe he says, maybe it was interesting to compare pointing performance against human evaluators too.
Yes, we can compare we can test more the pointing gesture systems and our system, but until now, the pointing gesture system is one of our best systems. It is very robust and we can use very well in our experiments. Until now, we are already integrating the systems slowly, but the pointing gesture system has a good performance for us. So we can do more tests and more comparisons with it. But for now, it's a very good performance for us because our focus is not in the system. Our focus is in the interaction, in how the human feels about the interaction with a virtual agent now. So yes, we can do more tests, but for now, it's not our focus. We want to use only good performances systems.
Okay, perfect. Okay, thank you very much, Ana Cristina. So we are going to go to the last presentation of this session. It's going to be the fourth paper then now. The title of the fourth paper is Aspects of Human-Robot Interaction in Autonomous Vehicles. Its presenter, it's going to be Nicolas dos Santos Rosa.
Hi.
I don't know if Nicolas is there. Okay.
Do you hear me?
Thank you, Nicolas. Yes, I can hear you. So the words are with you now.
Hello, everybody. I'm sharing my screen. Do you see the screen?
Okay. Yes, we can see.
Is the presentation changing?
Yes, it's changing.
Okay.
Thank you.
So let's start. Hi, my name is Nicolas Rosa. I'm a PhD student in the Laboratory of Systems, the Intelligent Systems at the University of São Paulo. And today I'm presenting our work, a survey on the aspects of human-robot interactions in autonomous vehicles. So here I'd like to present the outline of this presentation. And first, I'm going to briefly contextualize our work and the objectives for the addressed subject. Secondly, I will introduce you the autonomous levels. It is a key concept for our work. It was proposed by the National Highway Traffic Safety Administration, NHTSA. And then I will present the type of human vehicles interaction that we found out in the literature and how their design can be conducted. At the end, I will present your contributions. As long as the technical challenges are being fulfilled, researchers have begun to discuss the social and ethical aspects regarding the development of platforms that allow more interaction between passengers and autonomous driven vehicles, AVs, right? And in other words, after handling the technical challenge, the research are able to investigate the social aspects of such platforms and the human-robotics interaction concepts. We conduct this research since related works in the literature only present a summary of ideas discussed in scientific meetings and workshops. Our objective was to present a more structured and up-to-date perspective of the area, point out what is currently being studied to improve key aspects of such interactions, and how to design potential new approaches. The gathered information was presented in a survey manner, which contains the discussions, concerns, and prospects of the human-robot interaction field for autonomous vehicles. Nowadays, there is a great interest in developing such autonomous platforms. This is desired mainly from the public health point of view, since every year around the world, there are 1.24 million road traffic deaths, of which 9% are caused by the driver errors. Technology developed in this area and to take full control of the vehicle to do with the driving task. A key concept to understand our work is the automation levels proposed by the National Highway Traffic Safety Administration, NHTSA. These classifications, which level 0 indicates no automation and level 5 indicates full automation of the vehicle, were elaborated by the Society of Automotive Engineers based on the automation of the driving functionalities and the resource to enrich the user experience. On the right, you can see a description of each level of automation. And on the left, you can see some concept cars exemplifying the highest levels of automation. In this work, we identified 4 different types of human-vehicles interactions based on 2 criteria. The first one is how the interaction is established between the agent, human and AV, and the second one is the type of the technology involved in the interaction. They are, the first one is Advanced Driving Assistance System, ADAS. The second one, within vehicles interaction, internal interactions. The third, with vehicle interactions or external interactions. And the last one, it is the user interfaces, UI for automated vehicles. ADAS are automated systems designed to help to make driving easier and to help the driver to avoid accidents. And in general, they can be classified within the following categories. First one is adaptive, automated or assistance. It can be used for monitoring, warning, and driver support. The most popular ones are cruise control, ABS, and lane keep assistance, among others. Regarding within vehicle interactions, interactions that occur inside the vehicle, which non-driving related activities the user would like to engage in while on a ride in a highly automated vehicle. The reference research found out that users like to listen to music or radio, talk to other passengers, read, to work, watch out of the window, among other activities. This type of social experience also includes the interaction that the passengers can have with other people who may or not be present in the vehicle. Regarding the with vehicle interactions, the inclusion of a robotic agent might culminate in a series of confusing traffic situations for other drivers and pedestrians. Human-to-human interactions occur all the time, usually expressed as action of kindness toward others, what makes traffic more harmonious since they indicate their movement intentions. These interactions are in general expressed by gestures, eye contact, and light signals. However, how is these interactions be handled when there is no longer a human driver? Another type of human-vehicle interactions are user interface. One way to directly interact with humans is through visual stimuli. And user interface can use interactive screens are normally employed to perform this function. They can display relevant information about the trivial car status, like speed, distance travel, and amount of fuel. Or then they can display infotainment fields, allowing the driver to listen to the radio, to check the GPS maps, or to make cell phone calls. The present image here exemplify Waymo's user interface developed for different types of user. Here you can see different levels of detail of the technical information. Research have been designed the social experience for enforcing 2 aspects. The first one is trust, and some studies have investigated aspects such as safety, confidence perception, the reasons and consequences of overtrusting, and the incorporation of human aspects to UIs, name, age, voice, that can contribute for increasing confidence. The addition to trust, research have been concerned with interaction designed for recreation purposes, entertainment. In a highly automated vehicle, a direct impact for some drivers will be the loss of driving pleasure. This is a transition process of joy of driving to joy while driving. Concluding, in this paper, we present a survey about HRI in AVs, which can serve as a reference to the team, since it presents the history, the current panorama, and the future prospects. We proposed a structured way of categorizing the social experience by different types of human vehicles interactions existing in the literature. The paper also outlines which aspects of the user interface and experience and design are being employed by the automation process to overcome the problems of confidence in AVs and how to make the ride experience more entertaining. I would like to thank you all for your attention.
Okay, thank you very much, Nicolas, for your presentation. Now we are going to go to the questions. Let's see if somebody in the audience would like to ask a question. Or maybe somebody also, this presentation is being broadcast in a YouTube channel. We have no questions from YouTube for now. Okay, well, this is a very interesting topic. It's the number that you have shown us, the more than 1 million of persons that die every year in the world in traffic accidents is really savage. And of course, certainly in a close future, we will have autonomous cars in all our highways. And also this studies about the interaction with robots. There are a lot of interesting aspects as roboethics, for example, right? What are the implications of the ethics in the development of these robots cars? Yeah, for example, if an accident could happen, who is going to be charged for the accident? The robot, the guy, the company that builds the cars, or the system that it's going to provide the necessary structure for the highway? Because for making cars driving in highways, it is not only necessary that we could have autonomous vehicles. We have also highways that could be structured and conditioned for the cars. So, what are the prospects, the future prospects that you have found in your study for this human interaction with the cars?
Nice question. There is a very interesting work that points 4 major challenges that the researchers can focus to help develop in this area. The first one, it is research can focus on the safety aspect. So design interactions that you make the operator inside the car take actions that will always be a safe action. So even that the operator doesn't take you can take an action, but the platform needs to ensure that the action actuated will be safe. So there is this interest in developing more safe and robust platforms. So the research needs to guarantee that the interactions that the operator and the human will be safe, right? And a second aspect the research can focus is how to transform the car into a place of productivity and entertainment, because since the human is not in the main role of driver, the robotic platform you will perform that task. The driver you become a passenger or an operator of the platform. So which activities he can perform inside the car, and develop this interaction environment will be a very interesting research area for incorporating inside the interior of the car. A third aspect that you can focus, it is how the researchers can investigate how the driving and the mobility will change when these platforms or will be incorporated in the real traffic that we have today. How will be the interactions of the humans with these platforms? As I presented, today we have a lot of human-to-human interactions, but how will we interact with these platforms when there is no driver anymore, when there is no driver anymore, right? And
okay.
A fourth aspect, it is the research can focus on the privacy and security of the information that these platforms are collecting. Since the driver you take a more entertainer, you'll be inside in this entertainment environment. We can explore social aspects. The passenger can you'll be in a more connected environment, like he can work, he can access your social medias, but the platform needs to ensure privacy and security of this data, the user data, right? So these are some major challenges that researchers can tackle for this aspect.
Okay, thank you for your answer. We have Professor Marcelo that would like to make you a question, please. Professor Marcelo?
Hello, everyone. Can you hear me?
Yes.
Okay. First of all, I'd like to thank Nicolas, Rosa for his presentation. It was a great presentation. We could see many interesting things that are going to happen next years. But I would like to, it's a very short question. For the last 15 years, we are hearing things and seeing very nice videos and the challenge when it comes to autonomous cars. What's your forecast, Nicolas? When this will become true?
It is a very hard question to ask that, because I remember seeing a video of Sebastian Trum making a future prospect like 15 years ago, and we are still developing self-driving cars. But my position, it is that first we need to handle all the technical challenges. Here in this presentation, we are trying to make an active step. We are introducing these social aspects, this ethical, trying to understand that, trying to how can I say? We are trying to see which ethical aspects we encounter when we incorporate these vehicles on the roads. But maybe we can identify some problems that will change how we develop these platforms today. And it is interesting if we can detect this these social and ethical problems while we are developing these platforms. So I think, I don't know when they will be on the road. I will not make a prospect of that, but I'm just trying to highlight these aspects of trying to incorporate the social and ethical aspects on the development process.
Thank you very much, Antonio. Yes, I remember that 10 years ago when I was in Japan working, there was a team of humanoid robotics, and they used to construct humanoid robots, biped robotics, and they couldn't test the robots in Tokyo. They have to go to a city in Japan that was the only city in Japan in which robots could walk. So in other parts in Japan, in any city, it was not permitted for a robot to walk. So they have to transport all the equipment if they wanted to make the test in the streets for making robots. It was 10 years ago, more or less. Now things are changing, but slowly. But I think it's a necessity that this kind of technology would come. Well, thank you very much, Antonio, for your presentation, and thank you also to all the presenters, all the professors, all the students, all the public that are accompanying us in this session. Well, I will close this first session, and we will wait for the second session. Thank you very much to everyone, and good morning.
Okay, thank you, Fernando. We invite Josué for coming with the second session. Is with you, Josué. Many thanks for all of you. We have a bunch of people at YouTube watching us too, just for you to know that. Go ahead, Josué. Josué, we got some problem here with your sound. No, I still don't hear you. No, we are not listening.
Okay, you can go ahead.
No, your sound is cutting.
Luis, I think you can try to invite the first speaker, and in this time we try to solve the problem of Josué.
That's what I was going to do. So we call our first speaker on the second session of LARS. It's going to present the work Proteger, a social robotic system to support child psychological evaluation. And the work is from Hélio Azevedo, Diego Godoy, Roseli Romero, and Josué Ramos, Germano Filho, and Márcia Garcia.
Olá, vocês estão me ouvindo?
Yes, we are listening you very well.
Okay. I would prefer to use my previous presentation, a gravação que eu fiz, acho que fica melhor por conta do meu link que não está muito bom. Vocês poderiam ativar?
Sure.
Bruno, can you do that for us, please?
Yes, we can. Just a second.
Tomorrow I go to have a talk from Professor Gruppen from UMass. And on Wednesday, we are going to have a talk of Professor Luc van Gogh from Belgium. And he's going to talk about the topic in the last presentation, self-driving cars, vision for self-driving cars. So we are waiting for you to watch. And Professor Marcelo Becker will talk on agricultural robotics on Thursday for us. So Bruno, when you are ready in there, you please go ahead. And tomorrow night, we are going to have a cultural presentation here. We have a violin and flautists that will be, we intended to, we don't know yet, but perhaps we are going to have our best papers told in there. The best papers of LARS goes to DINT, the Journal of Intelligent and Robotic Systems, just for you to, and perhaps tomorrow in the night, we're going to disseminate who are the 10 best papers of LARS 2020.
Azevedo, trabalho no CTI, Renato. Olá, meu nome é Hélio Azevedo, trabalho no CTI Renato Arche e vou apresentar para vocês o artigo Proteger Social Robotic Systems to Support Child Psychological Evaluation. Contexto e objetivo, né? Este artigo nós estamos propondo um sistema colaborativo chamado Proteger, né, que usa um robô humanoide como um recurso lúdico no diagnóstico, né, de crianças, diagnóstico psicológico de crianças na faixa de 6 a 10 anos. Okay? Quais são as hipóteses levantadas nesse trabalho? Tá? O quanto um robô, né, teleoperado, humanoide, auxilia, né, o profissional a quebrar a barreira oferecida por algumas crianças em participar de sessões de avaliação. E qual é a aceitação do robô humanoide pelas crianças e pelos psicólogos? Bom, uma pesquisa bibliográfica, né, na Web of Science revela, né, que, inicialmente, nós temos poucos trabalhos, né, apesar de ser uma área muito interessante, né, não existem muitos trabalhos nessa área, né, e esses trabalhos acabam se dividindo, né, nas seguintes áreas, né. 27% estão associadas com autismo, isso é natural, né, as crianças autistas, elas se sentem muito confortáveis, né, em utilizar, em interagir, né, com os robôs, né, devido à resistência que elas têm em interagir com pessoas. Né. Aí nós temos 16,6% em cada uma das seguintes áreas, né, educação, né, os robôs utilizados, né, na área de ensino, aprendizado robótico, né, então o processo cognitivo de evolução, né, do ser humano é aplicado similarmente, né, nos robôs, uma grande preocupação com ética.
Acho que tivemos um problema. We have a problem.
disponíveis, né, na Web of Science. 18 artigos num período de 5 anos. Muito bem. Qual que é a abordagem tecnológica, né? Nós estamos utilizando, né, a técnica de mágico de Oz, né? No caso, nós temos um psicólogo atuando como um mágico que utiliza o robô Now como uma interface, né, para interagir com a criança, ok? Qual que é o ambiente, né, dos experimentos? Nós temos duas salas, uma sala de controle e a outra sala de entrevista. Na sala de controle permanece a psicóloga, né, que controla o robô Now como se fosse uma marionete, né? E na sala de entrevista nós temos a criança e o robô Now, ok? Qual que é a sequência, né, que é seguida nas interações? Inicialmente, a criança assiste um vídeo, né, com uma apresentação do robô Now. Nesse vídeo, o robô Now convida a criança a interagir. Okay? A criança tem a opção de ter um relacionamento, né, concreto com o Now ou não, né? A psicóloga faz essa pergunta, caso a criança deseje conhecer o Now pessoalmente, né, ela é levada até a sala de entrevista e a psicóloga fica na sala de operação controlando o robô, né, à distância. É interessante, né, é importante ressaltar, né, que a voz da psicóloga alcança o robô Now e tudo que a criança fala chega na psicóloga, né? Além disso, a voz é alterada digitalmente por um motivo muito simples, né? A criança não pode reconhecer, né, no robô Now a imagem da psicóloga, ok? Então o objetivo é a criança tem que ver o robô Now como se fosse um amigo, um alter ego, né? Aqui nós temos o vídeo de apresentação, né, que a criança vai assistir, né? É quase como se fosse um desenho animado. E aonde ela vai decidir se resolve ou não, né, interagir com o Now.
Olá, meu nome é Não. Eu sou amigo da tia Márcia. Acho que tenho a mesma idade que você. Gostaria de me conhecer?
Observem os aspectos lúdicos e brinquedos, né, que a criança vai conseguir reconhecer na cena. Bom, além desse vídeo, né, nós já sabemos que vai existir uma interface, né, um sistema de controle, né, remoto, onde a psicóloga controla o Now, né, a sala e a outra visão que o próprio Now oferece. Tá? Um conjunto básico de comandos, de movimentos, como, por exemplo, para se sentar ou levantar o robô, né, acenos, né? E além disso também temos mais uma seção aqui, que é a seção de avisos, né, que eventos relevantes que ocorram com o Now são reportados. Qual é a estratégia de avaliação? Então a criança vai interagir, como que a gente vai conseguir extrair informação para responder as duas hipóteses do trabalho. Tá? Inicialmente, a própria sessão, toda a gravação da sessão vai ser analisada, né? E além disso, serão aplicados questionários para a criança e para o psicólogo, né? Os questionários são aderentes à escala Ricarte, né, que classifica as respostas indo de 1 até 5. Okay? Muito bem. Os questionários. As crianças os questionários que são aplicados às crianças devem ser simples, né, e reduzidos. A gente não quer cansar, né, a criança. Então, basicamente qual foi o seu sentimento ao interagir com o Now, né, se ele ficou confortável ou não, né, se ele ficou com medo. Né? Você gostaria de falar com o Now novamente, né? E se você prefere falar com o Now ou com a psicóloga. Por outro lado, né, o questionário aplicado aos psicólogos, né, são mais complexos, né, e envolvem a aceitação da ferramenta e identificar a própria atitude do psicólogo na direção da robótica, né, se ele aceita passivamente o uso desse tipo de ferramenta. Okay? A avaliação dos filmes, né, da gravação da sessão, permite, né, você efetivamente identificar se a ferramenta é útil ou não. Né? Essa avaliação da eficácia é feita através de análise estatística, né, pela leitura dos sinais corporais da criança. Né? São 3 sinais que são relevantes. Né? A fixação do olhar, né, se a criança realmente está interagindo, né, está interessada na interação, a emoção que a criança apresenta, né, se é alegria, se é medo, né, se é um cansaço, e o número de palavras que a criança profere, né, o quão prolixa é a criança na interação com o Now. Bom, conclusões, né? 2 pontos importantes nesse trabalho é a originalidade do tema, né? É um tema que está iniciando as pesquisas, né? Que está iniciando as pesquisas, principalmente quando envolve casos de violência, tá? Violência infantil, identificação, né, das causas da violência infantil. E, além disso, né, ele é um projeto que envolve diversos profissionais, né, como psicólogos, né, profissionais da área da ciência da computação e da robótica. Infelizmente, né, devido à pandemia da Covid-19, né, durante esse ano, os testes práticos não foram viabilizados nas clínicas, né, e eles foram adiados para 2021. Tá? Um ponto positivo é que nós conseguimos, né, amadurecer a ferramenta, né, a interface de controle da psicóloga, né, principalmente considerando sua usabilidade. Como trabalhos futuros, né, uma funcionalidade interessante é a imitação dos movimentos da psicóloga durante a sessão, né? Então, o Now iria imitar os movimentos corporais da psicóloga, uma identificação automática, né, das emoções da criança, né, e fornecer essa informação, né, para a psicóloga durante a sessão, né, como uma informação a mais. E todo esse conjunto, né, de vídeos e de gravações que foram realizadas, elas podem servir, né, de insumos, né, para a construção de sistemas mais complexos, utilizando machine learning, com aplicações em entretenimento, educação ou, eventualmente, para um suporte adicional para os psicólogos. Bom, muito obrigado pela sua atenção, né? E nós temos aqui os patrocinadores, né, desse trabalho, né? O ICMC, o CTI Renato Archer, né? CAPES, FAPESP, CNPq, né? A quem eu agradeço. Até breve.
Muito bem. Questions? Não. Não. Vocês estão me ouvindo? Tá.
Agora sim, Josué, vai lá.
Okay. Hélio, despite questions, if you have any problem, please tell me.
Josué, your sound is very, very badly. I can hear you. I can hear you. Sorry, it's not working.
Go ahead.
Okay, thank you, Hélio, for your presentation.
Okay.
Do we have questions, please? Hélio, this looks like to be an integration, a work that integrates several institutions. Can you tell us more about that? Do you have a network that you mounted on that? I see that you have the CTI, the USP, and other institutions there.
Yes, I'm going to speak in Portuguese. It's more easy for me.
That's fine.
Existe o CTI Renato Archer, né? Nós temos uma unidade do NAU, né? Paralelo a isso, nós temos o ICMC. No ICMC, o Diogo está construindo a interface, né? Encerrou a construção da interface, né? Nós temos na PUC Campinas uma psicóloga que chama Solange, né? Que vai criar esse link entre o nosso trabalho e o acesso às crianças, né? E além disso, nós temos uma psicóloga que chama Márcia, né? Que ela trabalha no Tribunal da Justiça do Estado de São Paulo com assédio, né, às crianças. Então, de fato, esse primeiro contato, a proposta, essa ideia, nasceu de uma interação numa visita que ela fez ao CTI. Tá? Então, no momento, esses são os atores, né, que estão trabalhando nesse desenvolvimento.
Okay, and I have some other issues about, I think you have some ethical things that you should register in the Brazilian research system because you are going to treat with subjects.
Yes.
How was that? Was so difficult? Or that's...
Existe uma plataforma, né, chama Plataforma Brasil, né? Você cria, basicamente, é quase como se fosse um projeto FAPESP, né? Então, você cria todo um conjunto de documentos, você tem que falar quais são os riscos, quais são as consequências, você assina muitos documentos, né? Sendo responsável pelas consequências daquela interação que você está fazendo com as crianças, né? E esse é um processo lento. Esse também é um outro ponto, né, que pesquisas com humanos, né, são impactadas. Então, esse processo foi criado e, no momento, ele está sendo analisado, né? A gente está na plataforma e está sendo analisado. É o mesmo timing de um projeto que você coloca na FAPESP. Tá? Tem que ter paciência e esperar, né?
Okay.
Nós estamos nessa autorização também, né?
Yeah, this is, even inside the universities has been something that we have to deal about it, but that's fine. Okay, Hélio, I thank you very much for your presentation. And in the next, we are going to introduce our next speaker that will talk about human-robot interface for remote control via IoT communication using deep learning techniques for motion recognition. The work is of Dieisson Martinelli, Jonathan Cerbaro, André de Oliveira, and Marco Teixeira. Please, somebody in here to present the work. Bruno, do we have the video?
My name is Dieisson Martinelli. I am a master degree student in postgraduate program of electrical engineer and Industrial Informatics at the Federal University of Technology, Paraná. The work was developed in collaboration with Professor André de Oliveira, Professor João Alberto Fabro, Jonathan Cerbaro, and Marco Antônio Simões Teixeira. The project theme that I will present is Human-Robot Interface for Remote Control via IoT Communication using deep learning techniques for motion recognition. Gestures recognition techniques have already been implemented as a way of controlling a robot to replace industrial methods where specific equipment is needed. These methods are safer and economic because this method does not have specific equipment. However, it is still necessary for the operator and all equipment to be present at the operating place. This is due to the type of communication connection between the components, since they all need to be with the same network. The objective of this project was to apply the MQTT protocol to develop communication via IoT between the components necessary for an operation. Thus bring not only more safety but comfort for the operator, who can do his job from any place and any machine. Bring safety and better transport logistics for the equipment, as the heavy processing machine will not be necessary to transport to the place of operation. The strategy is based on dividing each operation process into layers: operator, processing machine, and robot. Each layer is in a different network, communicating through MQTT topics, and each with a different function. This communication is managed by Mosquito Broker, which is a server that receives all messages from customers and forwards them to the relevant target customers. The operator layer is responsible for collecting the image of the operator through a camera. That image will be sent through an MQTT topic. The operator layer is also responsible for reading a MQTT topic that brings the image of the current view of the robot, that is then shown on the operator screen. The processing machine layer is responsible for all heavy logical processing. This layer is where the RGB image from the operator's camera is read and interpreted. In this image, OpenPose is used. OpenPose uses computer vision techniques to identify from RGB image data such as human body and hands. OpenPose identifies 21 different points on the hand. These points, they are the same for the left hand and the right hand. To apply linear speed, the strategy is to read the data with your left hand. The best strategy was to use a single finger to control the linear speed. For this, the index finger was chosen. The strategy is to use 2 tips of the index fingers to send commands to the robot. We use points 5 and 8. So every time the index finger is bent, an angle between these 2 points is impaired, and from that angle, linear speed is applied. For the application of the angular velocity, the same strategy is used, but this time the right index finger is used. The function used to calculate the angle between these 2 points was 8 and 2. Here we have an idea of the complete process of this layer, where the operator's image is received, it passes through the OpenPose, then the curvature of the fingers is calculated, and the angular and linear velocity are set, which are converted to the MQTT topic and sent. The robot layer reads the MQTT topic that brings linear and angular speed and writes it in a ROS topic responsible for the movement. It also sends the RGB image of the robot to Vision, using the same techniques as OpenCV for conversion, as already explained in the operator layers. Latency test and missing data were performed 1,000 times to obtain a better result. In the data loss test, it was proven that all packages reached their destination with 0% data loss. As latency is the time that the data packet takes to go from the source device to the destination device, the obtained time value was divided by 2, registering the latency time. For the latency test, it's possible to observe in the table the statistical parameters of measure value in our operation. The tests were carried out with 3 different machines connected to different networks. The operators in Rio Grande do Sul, the processing machine in Santa Catarina, and simulate robots in Santa Catarina. Although the latency values seem high at first, when testing method using IoT communication in simulated robot in order to get from one point to another, in comparison with a method that also uses gestures for control but without IoT, it's possible to observe that average time difference obtained was not very high, just 0.25 seconds, and the trajectory remained smooth. When using IoT communication, it's possible to carry out the entry communication process with significant losses and delays in communication. Even if the latency was a little high at the beginning, it's possible to find in the literature latencies with the same average obtained by this work for similar implementations. As a result, the benefits of using MQTT protocol to implement IoT in conjunction with ROS are evident. With this, more significant advantage is obtained in the logistics of transporting equipment in external operation, reducing the number of equipment. There is also a financial advantage, since no specific equipment such as control is needed to implement this strategy, and keep heavy processing equipment out of harm's way. In terms of security, we can point out that there is no need for the operators to go to the location of the operation, being able to control from anywhere as long as he has access to internet. Thank you.
Okay, we thank for the presentation, and as this is a video, please, we ask who has some question to forward the question, and we can get in touch with the authors and send the questions for them, okay? In the next, we call our next presenter. That will present the work called Rosanna, Robot for Social Interaction in Unstructured Dynamic Environments. The work is from authors Pedro Paiva, Murilo Batista, Marcos Cruz, Germano Beraldo Filho, and Josué Ramos. Please, Josué, are you going to present it?
Hello, good afternoon. I'm Murilo. I'm going to put a video here to play, okay? Please
fine,
tell me if the video is running, okay?
That's fine. Go ahead.
Good afternoon. My name is Murilo Batista, and I'm here to present our robot project, Rosa.
Is it appearing? The video?
Yes.
Yes, is it running fine?
For
okay,
me, yes.
Thanks.
Good afternoon. My name is Murilo Batista, and I'm here to present our robot project, Rosa, robot for social interaction in unstructured dynamic environments. This is a short index of this presentation, with an introduction, a talk on Rosa, a proof of concept, and a conclusion. When I talk on socially interactive robots, we're talking on robots which are able to communicate with people and to follow social norms. Doing those following of norms, however, involves some tasks that involve high processing power, such as recognizing people and objects. These are some examples of socially interactive robots. Here we can see Pepper, Kiwi, and Cosmo. And here we're presenting Rosa, robot for social interaction in unstructured dynamic environments. Some of Rosa's characteristics are perception given by a cloud system, verbal and non-verbal communication independent of the agent, and an integrated proof of concept. Here is a general overview of Rosa's mechanics. We have a binary 3DX, which serves as a mobile base and has sonar range finders, a Hokuyo laser rangefinder, a CPU which communicates with all the system and is when it is Rosa's brain, a Microsoft Kayak 1, which is used to recognize people and objects, an emergency button which is needed in cases of robot applied in real life, because we don't know what kind of emergency can happen that involves stopping the robot, and a virtual agent named Anna. Although the Pioneer 2DX already had sonars, it's important to use a Hokuyo laser rangefinder because it has greater range and precision. However, we are not disconsidering totally the Pioneer sonars because there are some glass doors in the environment we are going to test. So having a sonar is pretty valuable for this specific case. One key characteristic of Rosa is using cloud robotics. We are considering here cloud robotics as any automation system that relies on data or code from a network used for robot. And so we have here perception as a service. We're calling this term on the same vein of robots as a service, because we're talking on having perception, processing, done on a cloud. Specifically, doing real-time RGB, RGBD recognition and boosting learning. This is an image that illustrates cloud robotics in Rosa. We have Rosa's mobile system, which was what I've shown before. It's cloud and the environment. So Rosa takes data from laser and RGBD from the environment, sent through Wi-Fi to the cloud, which processes by their GPUs some techniques like OpenPose and YOLO, and sent by Wi-Fi where are people's skeletons, where are the objects in the camera, in the image, to Rosa's mobile system. Visual perception is key to social interaction, as we can take many nonverbal cues and recognize people, not only that are people in the environment, but also their faces. Actually, Rosa is able to recognize objects using YOLO, people's skeletons using OpenPose. Also, we are able to recognize people's orientation from the skeletons made in OpenPose using XGBoost, which is a paper which will be presented here in LARS by Pedro Paiva later in this conference. This is an example of visual perception running YOLO. So Rosanna takes RGB data from the environment. In this case, it's the image of those two people processed in the cloud, and YOLO recognizes two people and a handbag. And this data is sent back to Rosanna's mobile base, computer in this case. It's important when we have a social robot to have a social navigation scheme for it. For that, we are modeling people's social spaces, that is, spaces that represent limits where we can have specific kinds of interaction by asymmetric Gaussian functions. We have a simple following behavior, which is used just for the proof of concept. And currently we're testing timed elastic band plus A star using timed elastic band as a local path planner and A star as a global path planner. We are testing directly from Tab Local Planner, which is available in the internet for ROS. This is an example of an asymmetric Gaussian function. You can see that it is a skewed R2 Gaussian function. You can use this skew to represent not only the direction a person is facing, but also where the person is going to, making the skew bigger when the person is walking faster. Anna is a receptionist virtual agent which runs separately from the rest of the mobile base, which consists on a verbal interaction service, which is able to receive verbal data and communicate with the person through voice. Verbal interaction service, which recognize face.
Hélio? O que aconteceu? Alô?
Foi só um ruído. Pode seguir adiante.
Ok.
People's emotions, etc. An embodiment interface service which is still in development, which gives non-verbal cues to the virtual agent. So Anna would be able to wink, to say hi to a person with its hands. And a response management service which processes the verbal and non-verbal interaction services to give answers to the embodiment interface service of the kind of thing it should do. This is a short video of Anna in action. Anna was a project made in CTI some years ago. Let's keep the interaction here. So the person is communicating with Anna, requesting to register its name in the system. Next, we're talking on a proof of concept. A simple proof of concept which tests navigation and recognition capabilities of Rosanna in its actual form. It's a simple test of identifying and following a person, avoiding obstacles, and, if needed, changing the person which is being followed. We have a video to present Rosanna's initial tests. So there is Rosanna. Rosanna sends data of this person to a mobile, to the cloud. The cloud runs YOLO and recognizes the person. Being an RGB camera, it's possible to recognize the person's distance using both the Connect one and the laser rangefinder. As you can see, the robot goes to the person, recognizing it. It is also recognizing many screens in the room too. If the person gets too close, the robot backs away. In the second experiment, we have put a chair as a surprise obstacle for the robot. Hereafter known as dynamic obstacle. So Rosanna is able to control the dynamic obstacle and get to the person. In the third experiment, we look at what happens if Rosanna starts following a person and then another person enters. So Rosanna will start to follow the other person. As a conclusion, we are making here an overview of Rosanna's actual state. It is still under development. We plan to do more work in integrating Rosanna with the ANA virtual receptionist. And there is also some ongoing work with the cloud architecture in order to make processing faster. As for social robot, it's important to have real-time processing. Not that it's not happening in those videos, but these are cases where there was a single person or at most two people. We also want to process those people's skeletons and in the future recognize their emotions. So there are many things which will be needed to be processed in the cloud. Thank you for watching this presentation. Be free to do any kind of questions you wish. Thank you.
Josué, is our sound okay? I believe not. Okay, please, do we have any questions? Someone from YouTube, Bruno. Okay, Murilo, as this is also a work that involves interaction with people, I think I may ask you how do you plan to validate that together with public? Because you have done a lab work now. I think the robot is a size enough to have these ethical things. And how do you plan to do that?
We plan to do that by using Rosanna as a receptionist robot in CTI. So the robot will be able to approach people to detect if people are interested in interacting with the robot, and also making the robot walk side by side with the person.
Okay, thank you. You know that this is an issue that we should all be concerned with this. I mean, with if you have some aerial robot, we have the Anaki and so on doing that. But with terrestrial robot, we maybe don't have this laws done yet. So nice work. I wish to thank you, and we will try to move forward to go after the time that we lost some time. Thank you. Next work, a simulated environment for long-term interactions with episodic memory is a work from Isaque de Souza and Hélio Azevedo.
Oi.
Okay, Isaque, go ahead.
Pode colocar o vídeo, por favor?
Bruno, can you please?
Okay,
do you have it there? Oh, that's fine.
Oh. Actually, who is playing the video for us is Julio. So I'm asking here in the background just to start the video. So just take us a little second.
Do you have it there, Isaac? If you have, you can.
Oi, não tenho o vídeo?
Yes.
Ok.
Let's see who is going to be first. Okay, we got it.
Lobato Passos from Federal University of Rio de Janeiro. I am here to present the work, a Brazilian Sign Language
Eu
Video
acho que não é
Database
esse não, hein?
Proteger.
It's not this one, Bruno.
Isaac, if you have the video, I think it would be faster if you could play the video for it, please. If you don't, we're gonna have to look it up.
Please, Isaac, put your, if you have it there, please put your video. Bruno, stop it. Yes, thank you.
Isso, é esse mesmo.
Ok. Sorry. Let's go.
Olá, meu nome é Isaque. Eu vou apresentar o trabalho Um ambiente simulado para interações de longo prazo com memória e episódio, do Centro de Tecnologia da Informação Renato Arce. Aqui tem o roteiro da minha apresentação. Eu vou fazer uma introdução sobre interação humano-robô, robótica social e interação de longo prazo. Os trabalhos relacionados, uma visão geral do sistema, um simulador de ambiente doméstico, sistema cognitivo, resultados, trabalhos futuros. A interação humano-robô representa uma área de estudo na robótica com o objetivo de entender, projetar e avaliar sistemas robóticos que realizam interações entre humanos e robôs. Dentro da interação humano-robô está a robótica social, que estuda interações sociais entre humanos e robôs com o objetivo de aprimorar e enriquecer a cooperação dos robôs com os humanos. A robótica social é uma interface de comunicação entre os robôs, o agente robótico e os humanos. A robótica de longa duração é considerada quando o agente robótico, após ser implantado, mantém o engajamento das interações mesmo após passar o efeito novidade, mantendo o interesse das pessoas em realizar novas interações. No contexto, com o avanço tecnológico, aplicações de robótica estão se tornando comum, como acompanhante, cuidadores, recepcionistas. No entanto, a popularização dessas tecnologias aumenta o nível de exigência do comportamento do agente robótico, exigindo a adaptação no contexto de cada aplicação. Com esses desafios de criar sistemas inteligentes que aprimorem as interações e atuem em períodos de longo prazo, mantendo o engajamento dos usuários. A problemática em manter um serviço adaptado, ável e personalizado se aproxime de uma interação mais natural, se aproximando de uma interação humano-humano, considerando informações dos usuários e interações anteriores, com a diversificação de comportamento para a personalização da interação. O objetivo desse trabalho é desenvolver um sistema cognitivo com a capacidade de aprendizagem e memória para interação humano-robô de longo prazo. No caso, a memória para armazenar as informações das interações anteriores, e no caso, o aprendizado aprende com essas interações anteriores e com as informações dos usuários. Os trabalhos relacionados. O trabalho de Wang, ele desenvolveu um agente robótico que atuava como recepcionista e guia turístico. No entanto, ele armazenava apenas o nome dos usuários durante a interação. Então, quando o usuário fazia uma interação com um agente robótico, ele armazenava o nome e em uma próxima interação ele trataria aquele usuário pelo nome. No entanto, é apenas um tipo de personalização. Então, ele laboratórios de robótica e casa inteligente, no entanto, ele só fazia essa adaptação. O trabalho do Hus, ele atuou em 2 cenários, no serviço de segurança, no serviço num lar de idosos, onde ele, no caso, tinha um painel com cardápio, informações climáticas, e Na segurança, ele percorria um ambiente de escritório procurando indivíduos que estavam sem identificação e notificava a segurança. No entanto, o tipo de adaptação que ele realizava era a navegação adaptativa, no caso, evitando os locais que ele teve dificuldade para fazer o percurso e buscando os locais onde ele encontrava as pessoas que ele teve interação de sucesso. Também foi a única personalização da navegação. Aqui a gente tem uma visão geral do sistema, o sistema cognitivo e o sistema robótico num simulador de ambiente doméstico e uma comunicação utilizando ontologia. Selecionamos nossos personagens no simulador de ambiente doméstico. Esse simulador ele permite a interação social entre humanos e robô, no caso os personagens que estão no ambiente. No caso foram adicionados 2 novos personagens no ambiente com diferentes perfis, no caso um idoso e uma criança, e o controle dos personagens acontece de forma distribuída. Aqui, cada usuário controla um personagem e as instâncias ficam distribuídas semelhante a um jogo multiplayer. No caso, a Mariana é controlada pelo usuário, o José é controlado por outro usuário e o Antônio é controlado por outro usuário, de forma distribuída. E o agente robótico é controlado pelo sistema cognitivo. Aqui a gente tem uma demonstração, um vídeo de demonstração do simulador, os personagens no ambiente. Os personagens podem interagir, no caso, com o robô e com os demais personagens do ambiente e com os utensílios da casa, no caso, torneira, porta de geladeira, ambientes, coisas que estão nas prateleiras e na mesa, e pode percorrer todo o ambiente e interagir entre os personagens e o robô. Aqui é o sistema cognitivo. Sistema cognitivo utilizando a arquitetura cognitiva LIDA, que é um sistema de inteligência artificial geral. A arquitetura cognitiva LIDA está entre as arquiteturas que mais se aproximam da modelagem da mente humana, e no caso utilizamos para modelar o agente robótico. Ela contempla os seguintes recursos, de percepção, memória, atenção, interação social, planejamento de ação, motivação e emoção. O ciclo cognitivo, o sistema cognitivo é dividido em 3 partes: a fase de detecção de característica, a fase de pré-consciência e memória, e a fase de consciência e seleção de ação. A primeira fase, que é a detecção de característica, quando, um exemplo, a visão do agente robótico, quando ele vê um determinado objeto, essa informação é passada para o sistema cognitivo. E no caso, o sistema cognitivo identifica qual o objeto que o agente robótico visualizou naquele momento, e essa informação é passada para o espaço de trabalho, que é na fase de pré-consciência e memória. No caso, o espaço de trabalho consulta as memórias para saber se teve alguma interação relacionada a esse determinado objeto, mais informações relacionadas a esse determinado objeto. E os cotovelos de atenção, no caso, auxilia na seleção das informações mais relevantes relacionadas a esse determinado objeto e repassa essa informação para a consciência, que é o espaço de trabalho global. As informações na consciência, no espaço global, são propagadas para os demais módulos, no caso proporcionando a possibilidade de aprendizado, no caso principalmente da memória episódica. E a partir das informações da consciência é selecionado um conjunto de regras relacionado a essas informações que estão na consciência. E posteriormente é selecionado apenas uma ação a ser executada no ambiente pelo agente robótico. Foi realizado um experimento com sistema cognitivo utilizando memória episódica no contexto de lanches de bebida, considerando informações do clima, período do dia, estado de saúde do usuário, utilizando os mesmos personagens presentes no simulador, no caso a Mariana, o José e o Antônio, que apresentam diferentes perfis. Utilizamos o recurso de interface da arquitetura cognitiva lida para simular as entradas dos dados. E dessa forma, possibilitando a recomendação de lanches de bebida a partir de informações das preferências de cada personagem. E os trabalhos futuros, a integração do sistema cognitivo com o simulador de ambiente doméstico para ampliar os testes no caso do agente robótico e do sistema cognitivo. Obrigado.
Okay, thank you for the video presentation. And we are open for questions, please. I put in the chat, don't let me alone with the questions, please. Okay, João Fabro, please
Hello.
turn on your video and microphone and go ahead.
Hello, do you hear me? Do you see me?
Yes.
Can I ask the question in English or Isaque prefer em português?
Em português, por favor.
Ok, pode ser, Luiz?
Yes, go ahead.
Parabéns, Isaque, gostei bastante do teu trabalho. Tem a ver um pouco com a linha de pesquisa que eu trabalho aqui na UFSM de Curitiba, tecnológica. E a minha pergunta é sobre a questão da continuidade do teu trabalho, né, em que você comenta que vai colocar num ambiente at home, né, imagino aí um ambiente residencial, para que esse teu modelo cognitivo consiga interagir com as pessoas. Então, a pergunta é quais são as tarefas que você planeja dar, né, para esse agente cognitivo no ambiente de robótica doméstica.
Obrigado pela pergunta. E legal que tem outras pessoas também pesquisando nessa área. Ele vai realizar as atividades, pedidos dos avatares, no caso, os personagens que estão no ambiente, no caso, se pediu para pegar alguma coisa na geladeira, e realizar atividades programadas, por exemplo, colocar, talvez, uma roupa para lavar, que é uma atividade que ele pode perceber que tem que ser realizada pela quantidade ou por um período de tempo ele realizar aquela atividade. Seriam as atividades domésticas mesmo da casa, além das atividades, por exemplo, das pessoas, dos avatares do ambiente, solicitar determinadas atividades dentro da casa. Falar, pega tal coisa, ou faça determinada atividade. E também o ponto de diferentes perfis de cada usuário. No caso, porque tem um idoso, tem uma criança, e nem tudo que a criança pedir para o agente robótico realizar, ela pode realizar no caso. Então, estamos trabalhando mais ou menos nessa linha.
Ok, eu achei interessante essa questão de você falar das atividades que ele mesmo pode perceber, né? Porque o modelo cognitivo tem essa vantagem aí de ter a sua própria tomada de decisão e não depender apenas de ordens explícitas dos humanos, né? Então, achei interessante isso daí. Parabéns pelo trabalho.
Obrigado.
Beleza, Isaque, eu vou fazer uma pergunta para a gente poder encerrar essa sessão, passar para a próxima. Os robôs é mais relacionado à parte física, da construção dos robôs propriamente dito. Eu vi que você tem 2 modelinhos lá de robôs, né? Que vocês usam. Desses 2 modelos, um tinha um computador em cima, né? O outro vocês fizeram ele com uma carinha mais colocando coisa de papelão. Eu queria saber como é que o público vê isso. Se o público prefere robô que é mais realista, assim, que se aproxima mais de um robô mesmo, ou se eles preferem um robô mais disfarçado, né? Mais com cara de boneco, com cara de... Não sei se você entendeu minha questão.
Eu entendi. Na verdade, esse é um trabalho relacionado, que ele usa para guia turístico e ele tem 2 agentes robóticos. Então, ele só tinha a base, então ele colocou a caixa para utilizar 2 robôs. No caso, quando um tinha problema, ele tirava para manutenção e colocava o outro. Nesse trabalho, ele não relatou nenhuma diferença assim, nas interações com as pessoas. Apesar de um ser simplesmente uma caixa com a carinha e o outro ser realmente um agente robótico que tem até um braço e tal. Nesse caso, nesse trabalho, que é um trabalho relacionado, ele não relatou essa diferença de percepção das pessoas, no caso, compara com um robô.
E no trabalho de vocês pretendem fazer alguma coisa a respeito ou...
Então, no nosso trabalho, a gente está focado no comportamento do agente robótico, né? Então, ele vai estar no ambiente, é esse mesmo que está no vídeo, então estamos focados no comportamento dele para com as pessoas, se ele atende a necessidade, por exemplo, de uma determinada, ser solicitado para uma determinada tarefa, qual foi seu comportamento dele, consultando as interações anteriores da memória episódica, o conhecimento que ele tem sobre aquela determinada pessoa, sobre preferências, sobre os horários que a pessoa faz determinadas atividades, qual vai ser o comportamento dele quando algo assim, quando ele for solicitado.
Ok. All right, thank you, Isaque, for the video presentation, answering the questions. In the next, we go to our next session, and Professor João Fabro, who was a minute ago in here, will be the chair for this section. Welcome, João. It's on you now.
Okay, Luis Marcos, thank you. Let's welcome everybody from section Assistive Vision, Sensing, Mapping, and Path Planning 1, session VSMP1 from 11 to 12 a.m. We are 20 minutes late. So the first presentation schedule is waiter-bot comparison of fuzzy logic approaches for obstacle avoidance in dynamic and mapped environments using a laser scanning system. From Jonathan Cerbaro, Dieisson Martinelli, myself, and André de Oliveira. Jason is just trying to enter the room, but I think that we can, if you could play the video, the presentation, it would be better than wait for him. Bruno. Thank you.
Hello, my name is Jonathan Cerbaro. I'm a master's degree student in the...
Do you have it easy there? Okay.
Applied Informatics at the Federal University of Technology, Paraná, Brazil. And this work was developed in collaboration with Dieisson Martinelli and the supervising professors André de Oliveira and João Alberto Fabro from the same program. In the development of a robot capable of performing the function of a waiter at a social event, we needed to define the best approach for linear and angular velocity control so that our mobile base performs the obstacle avoidance in an efficient way. This motivated the execution of experiments to determine which of the usual approaches has the best performance in general, not just limiting the study to this specific robot. The 3 approaches compared are implementations of fuzzy logic for avoiding obstacles in an unmapped environment, where the obstacles have dynamic behavior like people walking around the scenario. The distance and direction data of the obstacles in the vicinity of the robot are collected through a 512 segment LiDAR Hokuyo sensor and then sent to the controller via ROS messages, where the fuzzy logic calculates the linear and angular velocities to be employed by the robot in order to avoid collisions and reach the final goal in the shortest time. The first approach for handling data collected by the LiDAR seeks to infer the velocities based on the nearest obstacle. The data is processed to find the nearest object, and based on its angle relative to the robots, the avoiding is made to the opposite direction. If the object is perfectly in front of the robot, the avoiding is made with a clockwise rotation. Angular and linear velocities are calculated as a function of the distance from the nearest object and its angle, thus being a fuzzy system with two inputs and two outputs, and with the linguistic variables defined as shown in this figure. This implementation is simple and efficient in avoiding collisions, but the fact that it considers only the nearest obstacle means that it is not the most efficient in situations where there is more than one obstacle in the region and risk of collision. In situations similar to a hall, for example, this implementation will cause the robot to move away from one wall, go to the direction of the other wall, and then return to the first. This is an unwanted oscillation that makes the trajectory inefficient. The second implementation divides the LiDAR readings into three distinct regions: the frontal, right, and left. Unlike the first implementation, this is sensitive to up to 3 simultaneous obstacles and is able to weight the distance of each one separately. The fuzzy controller calculates the velocities based on the configuration of 27 rows, since it has 3 inputs with 3 categories each. This approach is efficient in navigating an environment with multiple obstacles and differs from the first by leading to less oscillations in trajectory, but at the cost of a greater computational load. The third implementation is similar to the second. However, this one subdivides the data provided by the LiDAR into 5 regions: front, left, right, and far right. The operation of this approach is similar to the 3-segment version. However, it allows the configuration of the fuzzy controller so that it gives less relevance to objects present on the far sides of the robot's path, since they offer less real risk of collision. A counterpoint of this implementation is that its configuration is more extensive. As it is a system of 5 inputs with 3 categories each, there is the need of setting 243 fuzzy rules for each of the 2 outputs, considerably increasing the computational load. To determine which one of the approaches has the best performance in different applications, 2 experiments were designed. The first one is based on subjecting the robot to specific obstacle avoidance situations. The tasks were simulated in environments containing 13 obstacle configurations, 10 of those being static and 3 being dynamic, involving people interacting in different ways, according to the figures presented. The variables analyzed were the execution time and total travel distance, as well as oscillations in the trajectory. This table shows the execution time performed, emphasizing the 3 cases where the performances differ significantly. The performance difference is relevant when observing the execution time of the tasks. In terms of total distance traveled, the values are practically the same. In a narrow passage, the fuzzy controller number 1 was unable to detect the pathway and treated it as an obstacle, avoiding the passage, unlike the other two systems where the obstacle was overcome. When following the side of a wall, the fuzzy number 1 and number 2 systems treated the wall as an obstacle, seeking to move away from it at all times, applying angular velocities to the robot and delaying the task, in addition to causing oscillations in the path. The fuzzy controller number 3 ran along the side of the wall, treating it as a straight line. The oscillations in the angular velocity can be seen in the graph in relation to the time of each control system. The difference in perception capacity was better observed in the avoiding of a human who crosses the path of the robot diagonally. The controller fuzzy number 1 detected the human approaching from its left, so it avoided by rotating clockwise and followed a path to the right. But the person followed his path in a straight line, coinciding with the robot's new path. This behavior caused a brief moment where the robot followed the human instead of avoiding him. A similar behavior was observed in the execution of this task by the controller number 2. Only in the execution performed by fuzzy number 3 that this problem practically does not occur. This controller makes it possible to assign less relevance to obstacle in the far sides, which offers less risk of collision and therefore allowed the robot to perform a more efficient path to avoid the person. The second experiment involved a simulation of a social event with several static and dynamic obstacles, where the robot must deliver to 5 tables while avoiding collisions. 5 different combinations of table deliveries were carried out, and these were executed by the 3 fuzzy implementations, where the execution time and the total distance traveled were measured. During the simulation, there are interactions with people walking and objects on the scenario. The execution of different combinations aim to obtain an average behavior of the controllers. The videos of the simulation, as well as the source codes, are available on the WaiterBot GitHub repository. The average distance traveled by the robot was greater for the fuzzy controller number 1, and practically the same for number 2 and 3. The most significant difference occurred on the average execution time, where the fuzzy controller number 1 made a faster trajectory than number 2, despite the greater distance traveled. However, the fastest algorithm was fuzzy number 3. Through the observations made experimentally, it is concluded that in situations where the computational load is not an issue, the fuzzy controller number 3 is the most efficient in every analyzed cases, being the methodology which causes less trajectory oscillations and fulfill the objectives in the shortest times. The real impact of the computational load caused by the greater number of fuzzy rows in relation to the other methods is yet to be measured. The fuzzy number 1 and number 2 are fast to implement, not requiring as much configuration as the fuzzy number 3, being recommended for fast applications such as quick experiments. For applications where the efficiency is more relevant, then the fuzzy number 3 is the algorithm recommended, since its complexity for implementation is rewarded by a significant increase in the robot's performance. Thanks for the attention. From this moment on, I am open to questions.
Okay, thank you, Jonathan. I think you can hear me now. And,
yes, can you hear me?
Okay, very well. Let's see if the audience has some questions, or maybe YouTube audience. Well, I would like just to give you the opportunity, Jonathan, to comment about your work. What was your objectives, main objectives, and if you intend to continue this work?
Good morning for everyone. First, I'm sorry for the delay. Answer the professor's question. The main reason for this project is to study for better strategies, so we can implement this on future robots on our laboratory. So we think maybe in some next competitions from RoboCup or some other competitions, we may have better performance in navigating some the scenario. It doesn't matter which kind of objects are there. So this is a very small contribution for our robot, but we think we may achieve better performance in the future given the results we've collected.
Okay, Jonathan, there is a question from Josué. Do you consider social distances on the controller?
Well, no, but this is a very interesting question. We didn't consider social distance, but this may be a very good suggestion for some studies in the future.
Any other questions? Well, then thank you, Jonathan, for your presentation. I didn't present myself, but as I asked the question the last presentation, I am João Fabro from Federal University of Technology in Paraná, Brazil. And I would like to ask for the next presenter of the paper, Trajectory Generation Module Design for Robot Manipulators. That is from Gabriel de Almeida Souza, Gustavo Souza Vieira Dutra, and José Jean Paul Tavares. Any of the presenters are here? So, likewise, what do you do now? Do you represent the video?
Hi, Fabro. We don't have the video for this presentation. The authors haven't contacted us, so I believe this is a no-show. I don't know. I'm not so sure. I'm assuming this is a no-show because they haven't contacted us, and we don't have a video, nor they informed us which author would be in the presentation.
Okay, so let's skip for the next presentation. The title is Intelligent Deep Control for Underwater Robots Using Artificial Neural Networks and Reinforcement Learning from Wallace Bessa, Gabriel Lima, and Lucas Cadengue. Are any of them here?
I think Lucas Cadengue is here. We have to promote him to be a panelist. Please, Bruno.
Yes, I just did it. I just did it the last minute. Very nice.
Okay, Lucas, do you hear us?
Okay, yeah, I can hear you. Okay. Does anybody hear me?
Yeah, we hear. Oh. Okay, you can start your presentation. Welcome.
Okay, just a second. Are you seeing it? Okay.
Now we see you.
Okay. So, sorry. Okay. Good morning to everybody. My name is Lucas Cadengue. I'm a master's student at the Federal University of Rio Grande do Norte, and my latest work is intelligent depth control of underwater robots using artificial neural networks and reinforcement learning. The underwater robot used in this work was a remotely operated underwater vehicle, ROV. He is used mostly for mounting, inspection, and repairing of offshore structures. the equations of motion for this robot can be expressed in relation to a frame of reference fixed to the body with the equation 1, where the vector v is the linear and angular velocity vectors, and the vector x represents the position and orientation with respect to the inertial frame of reference. M is the inertial matrix. K is the centrifugal and Coriolis forces vector. H represents the hydrodynamic effects, and vector G, the restoring force vectors, such as gravity and buoyancy. And the vector U is the vector of forces and moments. So in the case of the ROVs, it is possible to decouple the movement in the vertical direction so that the vertical movement of the ROV can be described with this simpler equation 2, where M is the mass of the ROV, and D stands for the perturbation of the system, and H is the unknown hydrodynamic effects. So due to the necessity of controlling the ROV remotely, the control system is one of his most important elements. And there are several strategies for controlling it, such as the traditional PID and some non-linear techniques like sliding modes control and feedback linearization. The latter one is the one that was used in this work. So the feedback linearization, saying it simply, is a technique that transforms a nonlinear system in an equivalent linear system by using a feedback. So the system in a closed loop is linear, but not the original system. So we work with the equivalent linear system, and with them we can use the techniques of linear control. Considering a tracking problem, this is the following control law of second order. And there are a few things that I like to point out for this strategy. It is needed to have a precise modeling of the system, and we have to know precisely the parameters of the system. Because of that, it is widely used in structured environments, such as industrial robotics, for instance. But this is not our case for the underwater robot, because there are some unmodeled dynamics, and there are also maritime currents or animals that can bump into the robot. So we have to use another thing to incorporate the controller to increase his performance. The strategy that we use in our work was to incorporate a neural network in order to predict the unmodeled dynamics and the uncertainties in the modeling. So why neural networks? Because it is a widely used technique, and it's bio-inspired and allows a non-linear approximation. And besides that, there are some works that shows that artificial neural networks can approximate the uncertainties of a model and can be incorporated in the specific case of nonlinear controllers, such as these works here. This was the architecture used in this work, a simple one hidden layer perceptron, and the activation functions were Gaussian functions. And there is a problem when you work with artificial neural networks, that is to specify some parameters of the network. In our case, we used a reinforcement learning approach to optimize the centers ratio of the activation functions of the Gaussians, so that we could have a better performance. Reinforcement learning is one of the 3 main types of machine learning algorithms, and according to Hake in his neural networks book, the learning of an input-output mapping is realized through the continuous interaction with the environment, trying to minimize a certain scalar index of performance. A way to describe this framework in an easier way was proposed by Robbins in 1952, and it is the multi-armed bandit problem, also known as MAB. His name is an analogy to the one-armed bandit, also known as one-armed bandit, which is the slot machine. And his goal is to maximize the mean reward in the decision-making problem. One way to illustrate that is with this little robot. He needs to maximize his reward in having his meal, and he doesn't know where to go. If he goes to the usual place where he have his meals usually, or if he chooses to try a new restaurant where he never went. So in this case, this is a simple question of two possible actions, but let's consider that are a larger amount of actions that he could take. If he chooses always to go to the usual place he have his meal, then he would not have a knowledge of all actions, and he might be stuck in a suboptimal action. But also, if he chooses to explore the actions indefinitely, he will not exploit the optimal action times enough. So this dilemma called as exploration exploitation dilemma is a problem for decision-making problems, and can be solved in several amount of ways. The algorithm that was used in this work is the UCB algorithm, and he is a way to solve this problem. The UCB algorithm, the upper confidence bound, was proposed by Lai and Robbins in 1985, and it works by calculating a certain upper confidence bound between all arms, all actions, and after that chooses the arm in which his bound was higher. Such algorithm is also known to work with a principle called as optimism in face of uncertainty. So what is that? The robot in that case would try all restaurants before trying to choose which one is the best. So he will try all actions, and then he would calculate a certain upper confidence bound and select the action. This upper confidence bound is defined by this equation 4, and in the action that is taken can be defined as the argument that maximizes this term, where Q of t is the mean of the rewards for this particular action, for each action, and this term is a term that that defines how stochastic or deterministic is your system. For example, the restaurants is a stochastic system, because you can go in a restaurant in a day where the food was not good, and some other day you can go there and the food is good. So it has it is stochastic. So this term is needed, because if you chooses only the mean of the rewards, if you go in a day where the food is not good, then you can bias your system and not try that action times enough for you to know if the action was actually good or not. So with this parameter C, we control how stochastic is your system. If your system is purely deterministic, then this value of C would be 0, and you always have you in all iterations you only have the mean of the rewards. But once the system is stochastic, and the more it is, then this term will be higher and will have more value. You need to know, you have to visit the restaurant more times to have a precise prediction about the meaning of the rewards. So in our problem, we create a decision-making problem by increasing, decreasing, or maintaining the center ratio of the Gaussian functions. And using this algorithm, we have these results. He converts to a value approximately 5.4 times 10 to the minus 2. And these were the results that we had. Here we have the tracking problem, the tracking, and the red line is only with the traditional controller, the feedback linearization, and the black is the desired tracking trajectory, and the blue is by incorporating the neural network optimized with the reinforcement learning algorithm. And we can see that the tracking was way better with the compensator. And here we have the tracking error that in which we also can see that it was a smaller error with the compensator. And with that, we also present the control signal. So we can see that even though we incorporate the compensator, the control signal wasn't a lot different than before, even though the performance was better for the tracking. So by concluding, in this work, feedback linearization was combined with artificial neural networks optimized using a reinforcement learning algorithm, UCB, in order to deal with the tracking problem of our ROV. Using numerical simulations, it was possible to observe the performance improvement in the proposed framework compared with the traditional feedback linearization controller, and also the utilization of the UCB algorithm for optimizing the centers had great performance. Thank you very much to all the presents and CAPES, CNPq, and my research team, Robo team. Thank you so much, and I'm open for questions.
Thank you for your presentation, Lucas. I don't know if there are any questions. I have one quick question for you.
Sure.
You do all your evaluations using a simulation environment, okay?
Sure. Yeah.
Do you think that these results would also stand in a more complex environment, such as the real world? What are your thoughts about that?
Great question. I tend to say yes, but in simulations, the things always goes well. We know that. The next step that I would take would be to try it with a different plant. I would try it experimentally to see if I can validate these results experimentally too. But I would say that these results, I have to see it to be sure, but I think these results will stand for experimentation. Thank you so much.
Thank you. We have one more question from Bruno, yeah?
Hi, Lucas. Congratulations on your work. Very well done.
Thank you.
It's more of an operational question. I would like to know how do you plan to do some real work, some real scenarios testing? I mean, do you have a laboratory infrastructure, or do you have an idea where you could experiment with your underwater robot or something like this? Thank you.
Thank you. So for the validation, I was because we don't have this kind of plant here in the university. So I was trying to change the plant to try it in using in robotics. There is a omnidirectional robot in our laboratory that I would like to try it there, but the obviously is not as good as trying with the underwater vehicle, but I guess I'll have to try that for now.
Thank you, Lucas.
I think, just my compliment, I think our advisor has some knowledge of people in Germany that could help you on doing that, no?
Yeah, he have, but we were trying, but it is kind of hard to do that. But we'll try for sure.
Okay, thank you again. And let's go now to the final presentation of our section. The paper's title is Fast and Safe Path Planning Method for an Autonomous Smart Walker, from Luiz Nascimento, Joelson Rocha, Victor Santos, Diego Pereira, Pablo Alcina, and Anselmo Frizera-Neto. I think there's one of the authors is here, yeah? I'm right? Luis?
Yes, yes.
Okay, welcome. You can start your presentation.
Okay, I will share my screen.
I think there is no sound, Luis. Anyone hears?
For an autonomous smart walker.
Okay, now it's working.
Hi, my name is Luiz Nascimento, and I'm presenting the paper Fast and Safe Path Planning Method for an Autonomous Smart Walker. A walker is an essential tool for mobility assistance of disabled people with reduced lower motor function. Smart walkers are more complete devices that include motion planning techniques to perform autonomous movement. As can be seen on this figure, we have the youth's cloud walker. It is an autonomous smart walker capable of sensing and interacting with the environment, promoting assisted mobility and rehabilitation to impaired individuals. Assistive robots, such as youth's cloud walker, have real safety requirements since they interact directly with the human body. So, for this reason, it's important the planning of path sufficiently far from the obstacles. And that's the why we are working with the probabilistic form method. The probabilistic form method, or PFM, is a sampling-based path planning algorithm with the main advantage of obtaining a path bounded by a sequence of bubbles, which guarantees a free obstacle region for safe maneuvers. This method has only two parameters. And the first one is the R-min, that denotes the minimum radius allowed for a bubble, and the K is the maximum number of children bubbles that a bubble with a radius mean can have. The probabilistic form propagates through the free space by expanding new bubbles on the surface of the parent bubbles. For each generation, new bubbles can be expanded on the surface of other bubbles as a BFS algorithm. Thus, the form propagates until some bubble encircles the goal configuration. A free obstacle path can be extracted from the phone by finding a sequence of overlapping bubbles from goal configuration to the initial configuration. And this structure is called rosary. The rosary is an important structure since it maintains the path with high clearance from the obstacles. Besides, it's possible to apply some path smoothing techniques, maintaining the path, the length of the bubbles, which guarantee the path safety. The goals-based probabilistic form is an algorithm based on PFM, which improves the searching time by computing less bubbles. It is inspired by the RT goal-based algorithm and also has two parameters, the R-mean and the value of the bias. For each iteration, a random auxiliary configuration QAux is sampled to find the new parent bubble. The method GBPF performs an exhaustive searching looking for the nearest bubble from auxiliary configuration. On the surface of this bubble, a new child bubble can be expanded, and the center of this bubble will be the nearest configuration between the auxiliary configuration and the surface of the parent bubble. Finally, the configuration QAux has a chance to be sampled on the goal configuration, and all steps are repeated normally. In this paper, we proposed a variant of the GBPF, the improved goal-based probabilistic form, the IGBPF. This method presents another way to choose the parent bubble, and it has the same two parameters. As well as GBPF, for each iteration, a random configuration QAux is sampled on the free space. But instead of finding the closest bubble among all bubbles in the phone, the new variation IGBPF makes a search only for the bubbles which has at least one child bubble on their surface. So this is the nearest bubble. Now the method will find which one of these children bubbles is the closest to QAux. Finally, on the surface of this bubble here, a new bubble will be expanded. Here, we also have the case when the configuration QAux is sampled on the goal configuration in order to bias the search. And for the last case, the configuration QAux was sampled here inside this bubble. And obviously, it is the closest parent bubble from QAux. But now, if the distance between the auxiliary configuration and the center of this bubble was shorter than the distance between all their children bubbles, the new bubble will be expanded on your own surface. Well, this whole process described in this method avoids analyzing and computing distance for all bubbles in the phone for all iterations, which decreases the searching time. Now, in order to compute the bubbles, we are using the concept of bubbles of free space, which make it possible to compute a volumetric region in the configuration space, but only using information from the distance from the workspace. For the computing of this region, we need to determine the minimum distance between the robot and the obstacle. In this case here, we denote this distance by dW. The smart walker is a robot with rotation. So if the walker moves from the origin point QC and travels to an arbitrary point Q, and if the translational distance or the rotational distance traveled by the robot was less or equal to dW, the robot will not collide with the obstacle. Finally, this region with a conic shape is defined as every configuration Q such that the sum of the translational and rotational distance from QC to Q is less than or equal to dW. To make possible the use of this conic region for those methods based on probabilistic form, first we need to calculate the distance between the center of this region and its bounds. This distance, denoted by RB, will be the radius of a new spherical bubble inscribed in this region. Now, in order to simulate the path planning for the cloud walker, we defined two maps. The first map, it presents only one possible route from initial to goal configuration, and it has a narrow passage. And for the second map, we have two possible passages. This first one is a narrow, which has a short length, and the second one is larger and longer. And in this table, we have here the parameters value for the algorithm. This figure shows the results for one simulation. We have the rosary found for each method in each map, and inside the rosary we can extract the path. For the first map, the rosaries look similar for all methods because there is only one narrow passage. So let's look at the second map. It is possible to observe that the methods present different rosaries in different directions. For PFM in figure D, the phone propagated through the larger space, which is safer. However, the path is longer. On the other hand, GBPF and IGBPF, they converged for the short passage, obtaining short paths. Here we have this illustration with the motion being performed by the robot with the path obtained by the method IGBPF. It's possible to see that the robot is maintaining the clearance from the obstacles. These tables present the results for 100 simulations to analyze path length, number of computed bubbles, and the searching time. As can be seen, PFM presented the worst results for all these cases, but this behavior was expected because PFM performs an approximated coverage of the free space, so a high number of bubbles are computed, and consequently the time is higher. Another feature is that these bubbles can be expanded for all possible passages, and large passages generate larger bubbles. So this increases the probability for the phone to converge faster by this space. And for this case, it will generate longer paths. In the process for the IGBPF and GBPF, the bubbles are guided by random configurations, but the goal makes the probabilistic form converge faster to the goal configuration. Returning to these tables, IGBPF and GBPF presented very similar results, mainly for the first map. On the second map, it's quite similar, but it's more clear to observe that IGBPF presented better results than GBPF. So, the computation of the new bubble with information from the workspace was important because now the methods based on probabilistic form do not require the explicit representation of the obstacle in C space anymore. And this makes the whole path planning process computationally possible. The three methods, PFM, GBPF, and IGBPF, they all were capable of computing safe paths, but the method IGBPF proposed in this paper was the one who obtained the best results. Finally, future works involve research to find algorithms to improve the search of nearest bubbles, always trying to increase the performance of the method probabilistic form. So, thank you very much for your attention.
Thank you, Luis, for your presentation. And now we are open to questions. I have a quick question. During your presentation, I was wondering if your approach can be generalized for a 3D world, such as trying to make path planning for drones. Can you comment? We are not hearing you, Bruno.
Hi.
Luis. Yes, now
can you hear?
Yeah.
Sorry, you can repeat, please? And can I answer in Portuguese?
Ok. I can ask you in Portuguese. Eu estava perguntando sobre se o teu algoritmo ele pode ser generalizado para um mundo tridimensional, por exemplo, para planejamento de caminhos para drones em ambientes complexos que tem que subir, descer escadas ou vãos.
Sim. Na verdade, nesse experimento que nós fizemos, utilizando o modelo do andador, ele é para um caso tridimensional. Ele, no caso, ele está trabalhando com o movimento translacional, né, e rotacional, e com isso nós conseguimos desenvolver essa bolha que representa essas 3 dimensões. Então, sim, é possível representar a bolha para diferentes tipos de robôs, inclusive para robôs com mais altas dimensões.
Ok. Temos uma pergunta aqui do YouTube, eu vou ler para você. Flávio, what's the main advantage of the probabilistic phone methods compared to RRT star algorithms?
Sim. Então, nesse paper, nós decidimos trabalhar apenas com esses métodos baseados na espuma probabilística, devido ao fato de que nossa aplicação são para robôs assistivos, né? Nossas principais aplicações são para robôs assistivos e elas demandam essa região de segurança. Então, esses métodos baseados na espuma probabilística, eles garantem esse caminho com esse high clearance, né? Esse distanciamento dos obstáculos, e os métodos baseados no RRT, como no caso do RRT estrela, eles são muito bons, né? São bem rápidos, eles conseguem obter caminhos ótimos, porém não é a principal preocupação, digamos assim, do método em gerar caminhos que se distanciam tanto dos obstáculos. E para a nossa aplicação, que são baseados nesses robôs assistivos, que tem essa interação maior com o ser humano, né? Nós passamos a trabalhar com esses métodos baseados na espuma probabilística.
Okay, thank you, Luis. If there are no more questions, I would like to thank you, everyone that is watching this session, and inform that we will resume at 2 p.m. after lunch in the same YouTube channel. Thank you all for attendance.
Okay, everyone. Just a heads up, we take a break for now until 2 p.m. when we resume with the afternoon sessions. It's going to be a robot soccer. There is going to be 3 technical sessions related to the robot soccer topics. Starting 2 p.m. Okay, so I'm going to keep the Zoom session open. So if you're going to attend to the afternoon session, you can keep yours as well. And we'll see you soon.
Thank you, everyone.